sometimes surprises within this chemistry, which you cannot foresee. So I thought that at 2009, normally the guanidine chemistry would stop on copper dioxygen in my working group. But since then, there were always some co-workers and some stipends to go on with this. And I would like to show you some kinds of chemistry in this circle. Just a short glance why we do this chemistry. So all these efforts shall serve to make models for tyrosinase. Tyrosinase is promoting the oxygenation of phenols to quinones, and this is involved, for example, in the melanin formation. So in this mice, it's not working, or the browning processes in fruits or apples and bananas. And in fact, the most important thing here in the inner side is that you have a dinuclear copper center bound by a peroxido unit and 3 histidines on both sides. So this is a bioinorganic role model which is given. And going a little bit more into the details, those who are not so familiar with the copper dioxygen chemistry, just to be quite short, you start with copper 1 on both sides. So all the biochemical stuff is just ripped away in this view. And the oxygen activation is happening by a one-step, or in fact, it's two-step mechanism, but normally you only see one step in this type of chemistry, where you have copper 2, and the oxygen is reduced to the peroxido moiety, and this is found in nature. But also there are enough models, for example, starting with the Tolman chemistry, where there is copper 3, and the oxides here in this case. And you can distinguish them by UV spectroscopy, Raman spectroscopy, and also XAS spectroscopy, to name some examples. What do they do in biology? So this is normally their most favorite substrate, the tyrosine, and this is in this CH position is activated, and one oxygen molecule is really inserted here into this CH bond formally, and one ends up in water. And then the next oxidation step, you come from the tyrosine to the catechol and then to the dopaquinone, which serves then as monomer, for example, for the polymerization finally to melanin and pigments in the long run. So here's a catalytic cycle. You start normally with a copper 1, the desoxy state. It's oxygenated to a peroxy unit. Then the substrate is coming in, some kind of phenol. There are dozens of phenols, which can be transferred to catechols and quinones. And it's important in nature, you have a proton management, as I would call it. So you give in phenols, but the phenol only coordinates as phenolate. This proton goes to an adjacent base. And then the next step, then that is the true hydroxylation step. This position is hydroxylated to obtain this catecholate. And then the next step, you get your proton back to generate from this hydroxide group water, and also to redistribute in the end electrons. So each copper takes away 1 electron from the catecholate to generate the quinone, which is released, and you obtain back the copper 1. So in this catalytic cycle, you have a full electron and proton management, so you don't need any additional reductants or oxidants. There are enough, there are giants in this chemistry, and I think we should name them. So for example, Kitajima and Moruoka provided the first models with this peroxo species, with starting with tris-pyrrolutol borates. So for example, at -80°, they isolated these species, and they were with this earlier than all crystal structures of biological type 3 copper proteins. So by this, they made a prediction how in biology, this active center would look like. A little bit later, so 10 years later, Codera, for example, again took a facial coordinating ligand, but bound to a binuclear ligand, and again promoted a peroxo moiety. But now this was possible to promote the reversible oxygen uptake, and to promote this at room temperature. Another room temperature model around the year 2000 made again use of tris-pyrrolutol borates, but now with CF3 function, because one of the decay processes is that this peroxide unit wants to rip off H protons somewhere. So these are normally positions which are attacked, and to shield them with CF3 drugs is a good possibility to make again a stable model. But in all these models, the problem is that these two models, they don't do anything. They're just stable peroxides. At this point in time, this was really great to have it, but normally the target of this chemistry is to use the biological role model to convert it to green oxidants or to green oxidative catalysts. And the question is again, is the peroxo the active moiety in the oxidation, or the oxo? So one point in between of this, here the strategy was having more and more complicated ligands. So there are dozens more in literature, which I cannot explain now due to the constraints in time, but there are two, I would say, philosophies you can follow. So you make more and more complicated ligands, as my group is also following, but you can also go to more, to simpler ligands and get them simpler and simpler, but then you have to lower down the temperature. So normally this chemistry is working at -80°, but if you go towards -120, then you can just take simple imidazole ligands, or even you can take -140, or I think 145 is the maximum at the moment. And then you can again obtain a peroxo complex. And what Danstech found some years later, if you then add a substrate and lower the temperature again, you can capture the bismuth oxido species. So with this really, really simple ligands, you have the possibility to mimic tyrosinase as well, but really having the essence, which is then active in nature to find as principle. And in all these years, there was some kind of balance that there are always some peroxo models, which were interesting, some oxo models. I'm coming to the oxo species, and really similar work in 2005 by the Steck group was using this diterbutyl diamine ligand, the DBAT ligand. This DBAT ligand also promotes a peroxo core, but if the substrate is added, because the phenolate is such a good donor, it converts to a bismuth oxide species, the O core in this case. This species is then performing the true hydroxylation step. So this was a really important result, that it might be that the peroxo is the active species, but it might also be that the bismuth oxo species is the active one. And after these results, more species came up. For example, again, this binuclear species from Costas, Lobe, and Casella, who showed in 2008 that also again here the hydroxylation is promoted by this copper-3 species. And in my time with Danstech and the postdoc, we found that guanidines are also quite useful in this chemistry, because with this species, we also observed tyrosinase-like hydroxylation chemistry. But here it's again intriguing to look into the detail. So for example, if you just take this bisguanidine, which I was working in my PhD, you don't have any activity. No reactivity with phenolates and no reactivity with phenols. If you use the same kind of donor, but with diamine, so for example, again, the propylene backbone is shown here, then if you take, for example, again, the phenolates, you make a CC coupling. So this seems to be some outer sphere reactivity, just the radical CC coupling. And if you use, again, the phenols, you obtain as well the CC coupling. And if you now mix these two ligands, so combine one large donor, which is sterically quite encumbering, and the small diamine donor, then you have the possibility to obtain such a hybrid guanidine, as we called them at that point in time. And with this hybrid guanidine, you indeed obtain the catechol. So here is tyrosinase-like reactivity at -80°, promoted by a bismuth oxo species. We showed this by XAS and UV spectroscopy. Of course, if you don't take the phenolate, but the phenol, then again, you have this type of outer sphere reactivity leading to the CC's coupled product. So the balance between the ligands, so the donor competition, if these ligands are sterically encumbering, if they are strong ligands, and how they interfere with each other are really important. So going a little bit further, until now, I just reported to you that there are models which can be stable or not, that they promote reactivity, but this was stoichiometric reactivity. So you add in 5 equivalents of substrates and you are happy if you can convert 1 equivalent of phenol to catechol, and that's it. But going towards steps which are more like real functional models, more important is to look at catalytic reactivity. And here, one of the first milestones was done by the Reglet group in Marseille, that they found this imine-pyridine binucleotide system to promote catalytic reactivity with a turnover number of 15 to 16. And a bit later, the Casella group promoted this rather complicated looking ligand, which promoted a turnover of 1.6, so a little bit more than stoichiometric. But until then, catalytic models were quite rare, until the Tuche group from Kiel was really super active, because they took this system as role model and they just cut off here. So they combined imine donor with pyridine donor, and in between they are now working on pyrazoles and triazoles and many more donor combinations, and they found a lot of catalytic models, which is quite intriguing for this chemistry. So there are still few groups working on catalysis in this chemistry. Going a little bit further now, there are still open questions after so many years of work. So which species is the hydroxylating one? Because there are numerous examples of peroxo complexes performing the hydroxylation, but also of oxo complexes doing the same reactivity. It might be that in nature, there is 90% in the equilibrium in this side and only 10% here, but in XAS and UV and Raman spectroscopy, you only see the 90% of this majority component. So this is not totally clear. Then it's important, if you look for the peroxo core, you have the possibility, here's one spin, here's one spin, so you can combine it to a singlet, to an open shell singlet, or even is there a triplet solution? So in case of the peroxo core, we should check for the spin state situation. And then it's also important to derive principles if different donors are really required to obtain efficient catalytic models in the end. Yeah, and what are the factors promoting catalytic reactivity? How can we care about the protons going away and getting back into the cycle? All this is still open. So if we now think, how can we address peroxo species and bismuoxo species? After my experience in the guanidine chemistry, I thought that it would be good to use also other ligands, perhaps to address selectively peroxo species. And with the bispyroxyl methanes, which we started to work in my habilitation work, we had the ideal tool in hand to really promote the direct synthesis of peroxo species, which are stabilized towards the bismuoxo species. Whereas in the guanidine chemistry, we always obtain oxo cores because they are again stabilized towards the peroxo core. Important to note, in Tuchek's work, normally there are peroxo species responsible for the hydroxylation. And I think one of the reasons, with most recent work, he had a turnover number of 50 within 1 hour, I think. So they are really fast and really efficient models. Going a little bit further now to the bispyroxyl methanes, because in that chemistry we learned a lot. This was our first model, which we published in 2013. We had 50 of these ligands with different substituents at the pyridine, different substituents at the pyridyl, and also substituents here, but only this model makes the reactivity we desired. So there are really subtle details in the ligand design to promote hydroxylation reactivity and to promote catalytic reactivity. So in this case, we found a room temperature stable peroxo species, which is able to promote the electrophilic hydroxylation reactivity. So we made a lot of substrate binding kinetics, as you can see, and we tested a lot of substrates. And from here, you can derive the Hammett equation. And we found that we have a row of -1, which shows that we have an electrophilic mechanism as in nature. And we found that we are also able to perform the hydroxylation of non-biological substrates as 8-hydroxyquinoline, which is a substrate which normally blocks normal biological tyrosinase, as I would say. So this was one of our important results at this point in time. And the ability to promote the hydroxylation is quite large. So we could really use all this phenolate, it's important phenolate substrates to make stoichiometric reactivity, so electron poor, electron rich phenolates, and also these more complicated substrates, for example, the phenolate salt of estrone, like a hormone, or the 8-hydroxyquinoline, which is a non-biological substrate, but also some kind of protected acetyl tyrosine ethyl ester. All these were hydroxylated in a stoichiometric manner. Going a little bit further, we were also able to promote the hydroxylation of estrone, 8-hydroxyquinoline, and this tyrosine ethyl ester and the normal standard phenol with some nice turnover. In today's world, we would say, oh, the turnovers and also turnover frequency, they are really slow. But in 2013, it was really a highly important result. Going a little bit further, we checked the spin situation of these systems, and we found that if we are varying, for example, the copper-copper distance and the oxygen-oxygen distance, we have a possibility to verify the hyperfine planes, how they are looking, for example, towards the normal oxo. So the oxo is shown here, and the peroxo is a little bit, a little bit in gray-red here. And you see that the peroxo is stabilized considerably, and that there is a considerable broken symmetry stabilization on it, which is quite important. So the broken symmetry solution implies that the both spins on the copper are talking to each other, but not fully, which means that there's always some spin on the copper. One can imagine that like this. And this is in 3D, and you can also turn this a little bit around. And we also calculated the triplet surface, and we found that the triplet is not so far away. Normally, there were calculations from other groups. They showed that the triplet is normally 10 or 20 kcal elevated. In this case, for our catalytically active species, it's the case that here is a normal singlet solution. This is a broken symmetry solution, and the triplet solution is only 3.7 kcal per mole over the singlet solution. So 3.7 kcal is not a lot. So it might be that this triplet surface is also important for the final reactivity we observe in the end. Okay, further steps, what can we do? Because we had 50 of these ligands, only one was active. We thought, how can we change our reactivity? Can we do anything here? No, we cannot do, it won't give any peroxo. Can we change a little bit here? Can we change perhaps some of these donors? And there are some possibilities. So for example, we can change the pyridine towards an imidazole. The imidazole is more biologically appearing. Or we can also add here in the para position, because this para position is not disturbing the substrate channel where the substrate is coming into the coordination. So we went to these two further derivatives of our bis-pyrazolylmethane ligands, which is shown here. So for example, we have now the peroxo species with this imidazole, and we could also characterize this by XAS and cryo-AC. And then we again took our favorite substrate, which is 8-hydroxyquinoline, and we found that it's a really active species. So we really observed high catalysis, a high turnover number of 14 in 20 minutes, which is amazing because the other system was quite slow. And we also observed the substrate binding kinetics. And from this substrate binding kinetics, it's like a Lineweaver-Burke plot, but not in this linear form. We can derive the intrinsic hydroxylation constant Kox. And compared between the pyridinyl peroxo, so the father peroxo or parent peroxo, to the imidazole peroxo, just the change of this single donor in the ligand enhances the catalysis or the hydroxylation reactivity by a factor of 8. So the donors are really crucial for these details in the reactivity. It's important to note that this reaction is happening at -80 degrees. And the real tyrosinase has a constant of 12 per second at 25 degrees. So 2.3 at -80 is not so far away from 12 at 25 degrees. I mean, we are 100 degrees lower in temperature. So we called it our catalytic vortex. Going a little bit further, just now changing from the pyridine to the carboxymethylpyridine, which does not change a lot, we thought, we observed that the stability was raising. So we got a half-life of 50 minutes at 25 degrees, again, characterization by XAS and cryo-AC. We observed again stoichiometric hydroxylation activity with substrate binding kinetics, also again Hammett correlation, and again with a rho of -1.2, indicating the electrophilic mechanism, which is important in this chemistry. And we went then on, again checking for the different substrates, and we saw that in the meantime, you can test a lot of these phenol substrates, methoxyphenol and all these names, but most intriguingly is this substrate, because it was reported that in some cases, this substrate is blocking the copper. So this means in our case, it's important to observe the reactivity and observing that's not blocking the copper, and also checking for the turnover number. And again here, the turnover number was increasing, and it was also getting faster. That was funny. So just by attaching towards the pyridine unit a carboxymethyl unit is enhancing the catalysis by a factor of 100, I would say, from 16 hours to 7 minutes. I mean, that's amazing. And we try to understand this. So at this point in time, this was the fastest tyrosinase model system, which we could then publish in 2017. So at this point in time, if you would have asked me if the guanidines or the pyrazolylmethanes are better, I would have said, yes, pyrazolylmethanes, they are the key to all this. And we made some important insights, but therefore we have to go again one step back, because pyrazolylmethanes have the complication that they have the pyridine as donor and the pyridinol as donor. If you are working with tris-pyrazolylborates or tris-pyrazolylmethanes, then all three donors on both sides are equal. So there is no problem. But in this case, you have the option that the pyridine is axial bound, for example, in this conformer. So we called it the conformer bis-bis. because the pyrazolules are forming the equatorial plane. Or you can just twist, for example, this donor. So now here the pyridine is in the plane, or you can twist both sides, or you can only twist once. So 9 conformers you can imagine, but after computational optimization, you end up luckily with 4 conformers. And we made a large study on this, a computational study, to investigate the energies, the spectroscopy of all these conformers. And we found that in the end, these 4 conformers are most important. And we also checked for the donor situation. And this is a little bit complicated slide, because first we thought that the donors are also characterized by the charge. So we calculated NBO charges on the different donors, and we found that the pyridines have always the more negative charge. So they are formally more basic, but in coordination chemistry, the basicity is 1 point, but the nucleophilicity is another point. And what you also get from NBO calculations are charge transfer interactions. So in green, we are showing here the numbers of the charge transfer from the nitrogen, the coordinating nitrogen, towards the copper. And so you get here, for example, 19, 20, and 11, which means that the axially binding pyridine is a weaker donor towards the copper than the pyrazolule. So this was the first hint. But to be true, the pyridine has also the longer bond length. So you are a little bit comparing apples with bananas. But if you now are looking for a coordination where the pyridine is also in the equatorial coordination, then you see, for example, here in this case, here you have an equatorial pyridine and an equatorial pyrazolule. The bond lengths are comparable, but again here, the pyrazolule donor is donating more, as seen in second order perturbation theory in the NBO calculations, which means that we got a hint that the pyrazolule, even if it's not so basic, is giving more electron density towards the copper. So this seems to be key here for the coordination of the copper within the peroxo core. Going a little bit further, we performed all this for this parent peroxo, as I would call it, and we then also performed it for the carboxymethyl peroxo, so the fastest tyrosinase model that we have in this point in time on this level of theory, which is quite a good level normally. And what we found, I don't want to force you to look at all these numbers. It's all published if you're interested. So we found in the end that it's good to have a ratio of the charge transfer between the pyrazolule and the pyridine. And for example, this is 1.36. So the pyridine is 36% weaker than the pyrazolule, which is significant. I would not talk about it if it's only 5%, but it's more important that this difference or this ratio between the different donors is increasing to 1.45 if you compare pyrazolule towards the new carboxymethyl pyridinol, which means within the core donor competition, the pyrazolule is the strongest, then comes the pyridine, and then the carboxymethyl pyridine. So in the end, here we could show that by weakening the donor ability of this pyridine, we enhance the catalysis and the stoichiometric hydroxylation. So really this fine-tuning of the screws in the ligands is really important for the catalysis in the end. Okay, looking now at the other side, I have to look at the time a little bit. We did a lot of chemistry in bis-pyrazolyl methanes, and we are still ongoing there. But today, to close the loop between all these efforts we did in this chemistry, I wanted to show you the latest result from our lab now with using the guanidines in this case, because originally we were working on bis guanidines, and we had hybrid guanidines, then we were also working with aromatic guanidines, and then we used different systems to mix them all up. So for example, with such a benzoylic amine position, or to switch between these two positions. There are a lot of guanidines which do not do anything. Yeah, I'm not sure if we would publish them in this chemistry, but they are interesting as zinc polymerization catalysis, by the way. So going a little bit further, I had a good student, or I'm still having her, but she's coming to the end now. I'm having a student in my group, Melanie, and Melanie invented this ligand, as we called it TMG benza. So there's a benzyl amine and the TMG tetramethyl guanidine group, and you can come to the copper 1 complex, and by oxygenation in THF acetylenediol, you can come to the bis-mu oxidose species, and calculations showed that this species is stabilized again by 10 kcal per mole compared to the peroxo species. So that's always an important result for us, if we only see an oxo at different temperatures, is this stay only an oxo, or do we just miss a para-oxo? And by the computation and also other methods, we know that with the guanidine chemistry, normally we get only oxo species, which is again important because we wanted to investigate if now these have a superior activity and if they also promote catalysis. As you might expect now, because I'm talking about them, yes, they promote catalysis, but it's really an interesting story because they promote only special substrates, but really exceptional substrate. Going a little further, again, together with a group of Michael Rübhausen in Hamburg, we checked again, for example, with resonance Raman spectroscopy for the breathing mode, which is shown here with O18 or 16. So normally you would have this. Then with Ivana Ivanovic, we performed ESS mass spec, and we saw that these complexes are flying as monocations, which is also rather standard in this copper dioxygen chemistry. And then we also did XAS spectroscopy and EXAF spectroscopy. And for example, here you see then that there are 4 backscatterers. So we have two oxygen atoms with 1.89 angstrom, and then we have the 2 nitrogen donors, and the next copper is around 2.7, 2.6 angstrom away. So also by XAS, we obtained the information that we really have our bismuth oxido species, which is important then for the next steps. Now going towards catalysis, normally we would just take a phenol, add in our complex, add in auxiliary base, which is important for the catalysis, as the Tucek group has already shown, and then come to the quinone. Problematic is that a lot of quinones are so highly reactive that they want to go on with their reactivity and you cannot really trap them. So normally you get them in the UV, but you cannot really quantify how much is formed and how clean it is and what are the other side products, for example. So this quinone chemistry can be sometimes in an organic way quite challenging, I would say. I talked to a lot of organic chemists and they told me autoquinones, oh no. Yeah, but we had to get through this. And so we wanted to check for the regioselectivity, because if you have just simple phenols, yeah, then you don't have to care about regioselectivity. But if you have, for example, bicyclics as indolols and naphthols, which come up in some minutes, then it's important to check for the regioselectivity. And we found in the literature, again from the Tucek group, they are quite inspiring, these works, that you, for example, can combine quinones with orthophenolane diamine to form phenazines in the next reaction. So in fact, you can use some kind of quinone, or you can produce a quinone in the tyrosinase analog hydroxylation, then add in, for example, orthophenolane diamine, and then in this, it's quite a rather simple condensation reaction, you obtain this phenazine. You need some more time, so we can warm it up over room temperature, and then you need 2 or 3 steps of carbon chromatography to really obtain it. Sometimes we even crystallize it in the end, but then you have really clean phenazines, which you can really purify and isolate in the end, which is good for this chemistry. Going a bit further, for example, we tested this 3 quinolinol. You obtain this, but it doesn't have a really nice UV spectrum. So, for example, if you take 8 quinolinol, you have a wonderful band at 410 nanometers, and from this you can quantify the formation of substrates. In this case, this is really not nice to see in the UV spectra, but by the combination with the orthophenolane diamine, you can obtain then this phenazine, isolated, make MS, NMR, and for example, crystal structures. So in this case, we obtain this product because here it's clear you can only perform the hydroxylation in this position, easy case. But if you take, for example, this kind of naphthol, then you have the possibility to form a quinone or this quinone, and this would give the straight phenazine or the bent phenazine. And what we observed was that we only get this. So in between, we have observed this. We could have observed both, but it seems to be we can only isolate this. You cannot see this in any case. Okay, we were thinking, okay, we have a bent phenazine, that's it. Then we went a little bit on. So for example, taking this different type of 1 naphthol and 2 naphthol, and for example, this 3 quinolinol, 4 quinolinol, and the 6 quinolinol. And here in this case, again, you have the choice. If you hydroxylate here, or if you hydroxylate here, here you don't have the choice. And again, we isolated this bent phenazine. And also in this case, you have the chance to hydroxylate here or here. And again, we obtained the bent phenazine. The yield does not look quite convincing because we go with a lot of substrate on this. So we take 25 equivalents of the substrate, and there is a high conversion, and there are numerous processes happening. So in the end, we were quite happy to have this yield, and this is the isolated yield after column chromatography. And then we convert it into the ton. So the turnover number could, in ideal case, be 25. In this case, it's only between 11 and 16. But these are quite complicated substrates. And for example, this product, it's the first method to synthesize in a quite easy way this elegant benphenazine. Why I am so interested in phenazines? Phenazines are, yeah, multitasking, I would say. They are anti-tumor activity, anti-cancer activity, anti-malaria. So they are quite interesting class of compounds, and I have collaboration with some biochemists on this, but I cannot explain here more. And so it's interesting to have access to a variety of new phenazine compounds by just taking other phenols and this elegant tyrosinase chemistry. So there are some side reactions, yes, but in the end we obtain a nice turnover number, and that is really based on the isolated yields. The problem is the UV spectra of this, you cannot really use them in between to quantify the amount of this stuff. So, and when we were now working on these bicyclics, we thought it would be also good to check for other bicyclics, and crystal structure we obtained as well. As inorganic chemist, you need a crystal structure really to show that it's a bent structure, just as proof. And then we turned towards the indolols. And for example, we have here the 4 indolol, 5 indolol, 6 and 7 indolol. And here again, here you only have one possible substrate. Here again, you have the choice to hydroxylate here or here. And we obtain then again the benphenazine. And again, here in this case of 6 and 7 indolol, we obtain in the end the benphenazine. And the turnover numbers are again nice. And here we have again the crystal structure. So it's quite intriguing. Why do we always get the benphenazine? There should be some reason. I talked again to organic colleagues in Aachen, and I asked them, is it logical that we are attacking here and not here? We look for the LUMO, for the HOMO, for the charge densities, if there are something to do. So there should be an explanation after so many substrates. It should be some logical explanation why we always produce benphenazines. And then in the end, we found the Fukui function, because the Fukui function gives an impression where the attack for electrophilic reaction can happen. So it's, you can calculate from the HOMO and LUMO function. And there's, for example, the electrophilic Fukui function and also the nucleophilic Fukui function. So for example, for the substrate 2-naphthol, we calculated now the electrophilic Fukui function. So here's the OH group, and you can hydroxylate here or you can attack here. It's hard to read. So here is 21, here is 0.7. On the next slide, it's a bit better to read. So this Fukui function recommends that if an electrophilic attack happens, it has to happen here. Okay. Just checking for totally different substrates. So for example, 5 indolol. Here again is the OH dangling, and again you have the possibility to make hydroxylation here with a Fukui function of 19.9, so almost 20, and here with 1. So the Fukui function is again recommending that an electrophilic attack should happen here, and indeed that's exactly what we observe. Going back the 2 slides, so it was I think it was this one. So if you check, for example, for this substrate, the Fukui function says yes, here should be the hydroxylation. And we did this for all our substrates, but I don't want to show this for them all. I have a summary of this, all the substrates, and then you have the different possibilities if you hydroxylate here and here. And normally there's really a quite clear preference for the 2 positions. And exactly the observed reactivity in reality of the isolated phenazines is really following this Fukui function explanation. And we were quite happy that this is the first time to make this regoselectivity in the hydroxylation as a conceptual, with a conceptual explanation. Going a little bit further, what are now the next steps? This has just been published. And then Melanie observed that normally she had to work at -80 degrees, at -90, which is usual in this chemistry. But we are in a collaboration with engineers, and the engineers always told us, it would be good to be at room temperature in some way. And Melanie was just going back the past to my own PhD origins, because then she took copper iodide, and with copper iodide you have sometimes problems with redox chemistry, but in this case she obtained the bismuth oxidose species, which was stable at room temperature. Totally strange. There were these typical oxo bands. Okay, this is a little bit too strong because here is the pi-pi star transition of the aromatic ring lying below. But these two bands are normally quite typical, and we made some more analysis of this, and we have cryomass spec, as I will show a little bit later. And so we have species here. There is an iodide as counter ion, or also a diiodide cuprate. Diiodo cuprate, I think it's called then. Nomenclature is such a thing. So it seems to be that the iodide is surviving the process of oxo formation. Normally these copper oxo species, it's copper 3, are highly oxidizing. We use them to oxidize substrates, but iodide is surviving all this. Going a little bit further, if we add in more copper iodide, the extinction coefficient is even raising. So it's good to have more copper iodide. So this would be just the normal 1-to-1 ratio of copper to ligand. And we were a little bit astonished that this extinction coefficient is so low. So it's not the fully formed amount of oxo species. Dan Steck always told me, please check for the full formation of your species. Otherwise you have some crap running around. And he also told me that iodide is always a problem. Yes, he's right. Iodide is a problem, but it also gives some new opportunities, which I would like to share with you in my last minutes. So we then observed that adding copper iodine is really beneficial. So there is more oxo species formed. Now coming to the cryomass spectrometry, we see that, for example, the oxo is flying on the left-hand side really as a monocationic species. So the pure oxo with one iodide flying with, or it can also fly again with the cuprate anion. So we have the oxo core with a cuprate flying, giving a nice isotopic pattern. So it seems to be that this iodide is surviving all these processes. Then we were checking why is all this happening and why is the additional the addition of copper iodide so beneficial. And we found that there is some kind of equilibrium because we can form this monochelate species and also some kind of bischelate species. And then there's again the cuprate form. And it seems to be that iodide loves to form cuprates. Sometimes you also see in literature as copper 2, I4, 2-, and even larger assemblies then. And this seems to be what we also observe in NMR. So for example, you can prepare this monochelate complex, which is shown here in the first line. You can add copper iodide and then also make an NMR. And you see that, for example, this dimethylamine is a little bit shifted. Here the CH3 group is a little bit broadened, the guanidine is broadened. And if you make directly the bischelate just by having a copper ligand 1-to-2 ratio, you can obtain this bischelate. And again, the guanidine moves a little bit, the benzoylic CH2 moves, and the methylamine groups are also moving, which means that on the NMR time scale, we can really isolate or have them as isolated species. But it seems to be that these species can interconvert. So if we add to this more copper iodide, then we turn it towards this. If we add in again more ligand, we can turn it here, which leads us to the next experiment. So if we start, for example, with the original oxo with the catalytic activity, which I showed you with, for example, a PF6 anion, what happens if we just add iodide? Yeah, we can do this, and it goes down in the extinction coefficient, yeah, but it's still there. It moves a little bit. It's a small blue shift, which we are just investigating by TDDFT. And what we observe, this was happening at -90 degrees. And if you warm it up, normally it dies at -70, -60 degrees. You cannot do anything. After some minutes, it's dead after these raised temperatures. And finally, if you now add in iodide and you observe this species, now you can warm up and it will live for more than some minutes at room temperature. So this iodide has some interesting function. It seems to stabilize the copper core. Here's one of our first pictures from DFT. So the iodide sits really on top of this copper oxido species. And from my old PhD days, we have already crystal structures of not the copper 3 core, but the copper 2 bismuth hydroxide species, where again iodide is on top of this sitting. So an iodide can indeed survive the whole process of oxocore formation and further reactivity, which means the iodide stabilizes the oxocore, but it enhances also catalysis. So one of these last large tables, we again checked for some substrates, for example, 2-naphthol, 3-quinolinol, 6 quinolone, 5 indolol, 6 indolol, and in the end, we got better yields. That is quite funny because now we can work at room temperature. So in fact, it's for an organ, from the point of an organic chemist, it's quite practical. You don't have to go to -90 degrees. You can just put it all together at room temperature. You obtain intermediate, the bismuth oxide species. You can add your substrates, or you can also do it at a one-part reaction. And the yields of this interesting phenazine species are higher. So this is an important result that the iodine is making chemistry a little bit more complicated, but here it's also useful. With this, I'm coming to the end. I hope I could show you that with interesting peroxo species, with bispyrazole methanes, we could start into this chemistry because by this ligand we can tune stability and activity, and that the donor difference is really important for the catalytic activity, but that with guanidine complexes, after all these years, now catalytic hydroxylation is also possible, which is quite a surprise for us. And in this case, it's hydroxylation really proceeds via the bismuth oxo core. So the balance, what is the active species, peroxo or oxo? I think at the moment it's quite balanced between these two. So I cannot answer what is now the really active species. For the guanidines, it's the oxo core. For the bispyrazole methanes, it's the peroxo. But in nature, this question is still open. We could obtain bent phenazines from naphthols, quinolinols, and indolols. So challenging new substrates for this chemistry, which could be explained by the Fukui function. And we observed that with a strong halide influence, we can observe even more efficient catalysis. What we are planning, okay, we are going on with peroxo and bismuth oxo species, and also studying the catalytic cycle theoretically, and also applying electron transfer and charge transfer methods in this chemistry. Okay, this would also not possible without all the financing. So first I have to thank the GFG, the German Research Foundation, because all this work started in our Forscher group in these old days, in the SFB in Munich, then took over in the SFB here in Aachen, and our priority program, reactive bubbly flows, together with the engineers. They always want to have large quantities and high temperature, so this iodide species is quite good to go to room temperature. And also I would like to thank the collaborators, Ivana, for example, and Michael Rübhausen and Matthias Bauer for all these collaboration efforts in intriguing methods. Yeah, Alexander started this method, Alexander started this bispyrazole methanes with me in Dortmund, then Claudia took over in Munich, Patricia took over, has also her PhD there now, and then Melanie, she's on the photo here, she started all this guanidine chemistry in Aachen and had this exceptional substrate diversity, which she found, and so I have to thank my group, and I have to also thank Sigga and Eva again for organizing this, and I'm happy and looking forward to your questions. Thank you very much.
So I would love to give you a clapping sound now, Sonja. So thank you so much for that talk and to show us how that evolves and continues to evolve over all these years. And that's really a big and exciting field. So it's open for questions. And I actually already saw one popping up in the middle of your talk, which is by Anindya Zakar, and he or she, is asking if there are any sort of interactions between the kappa 3 centers, metal or metal spins, in the kappa 3 bis mu oxo complexes, yeah.
Sure. There are no Greek letters in this chat. That's really a problem. Okay, thank you for this question. Yeah, that's a good question. In copper 2, you have D9, D9, so one spin on every copper. But in copper 3, you have D8, D8. And so all spins are paired. The bismuth oxo species are fully singlet species. We also calculated the triplets, but the triplets are energetically really high. So that's a full D8 solution with all paired spins, not between the metal, but at the metal. I hope to answer your question with this.
Okay. Kalol has a question, so I hope I can get him here again. So here he is.
Hi, Kalol.
Influence is quite can you hear me?
Yes.
Yes.
Okay. So your iodine